This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is entropy change of an ideal gas. In this example, we're given that we have 2 kilograms of air, and we start out with a known pressure, 200 kPa, and a known volume, and we're heated to 500 C at pressure equals constant. So here's a picture of a pressure equals constant process on a PV curve. As temperature goes up, the volume is going up from state 1 to 2. We're going to look for the entropy change using the gas tables and using Cp equals constant theory. For part A, the gas tables, the entropy change depends on something S super 0, that's an entropy change at standard conditions, and there's a fix-it term for the pressure. Anyway, we're given final temperature, but we don't know an initial temperature. The first thing we have to do is find that initial temperature, and we can always pull in the gas law. So this is the specific gas law, pressure times volume equals mass times specific gas constant times temperature. Here I've solved for temperature 1. Let's do the calculation. The initial pressure, actually the pressure during the whole process, is 200 times 10 to the third newtons per meter squared. The volume is 0.8 meters cubed, 0.8. The mass, we're told, is 2 kilograms. The specific gas constant I'm going to construct from the universal gas constant, 8314 joules per kilogram mole. And I'm going to divide that by the molecular weight of air, which is 28.97 kilograms per kilogram mole. All right, when I compute that, I get 279 Kelvin. So that's the initial condition. That's the first temperature, T1. All right, now we can think about using the gas tables to, and the gas tables always, for entropy change, involve this relationship. Gas tables for air, I'm going to write down some values here. I'm going to have temperature, I'm going to have the S super 0 value we're looking for. It's in kilojoules per kilogram per Kelvin. And the first temperature is 279. The other temperature we need is T2, that's T1. We're told it's 500 C. Let's add 273 and make that 773. So this is going to be 773 Kelvin there. And then we'll fill in these values from an appropriate table. Let's go find a table. Here's table A17 from a book. Ideal gas properties of air. Now there's several columns here. The temperature goes down this way. We're going to use the last column, S super 0, but let's take a minute to talk about the other columns. I've got enthalpy, which is a function only of temperature in ideal gases. I've got something called P sub r. That's a relative pressure. It is not a pressure. It has no units. Over here is internal energy. That's a perfectly good thing. It depends on temperature. And this is V sub r. That's a relative volume. We'll later learn about that, but this is not a volume. This P here is not a pressure. These are dimensionless quantities, relative pressure and relative volume that we'll get to later. Here's the column that we want, S super 0. The first temperature we need is 279. It falls in between these guys. So the S super 0 value we need falls in between there. It's 1.6 something. The other value we need is 773. The bottom column is 570. Over here the temperature picks up again. 773 is between 760 and 780. So the S super 0 value is going to be over 2.6 something. So I've taken these values, I've interpolated. Let me put back over here what those values are. And these are the interpolated values. At 279, S super 0 was 1.6291. You can check my interpolation. At 773 in temperature, S super 0 is 2.6802. All right, so now we're ready to do the calculation here. Let's have one comment. This is a constant pressure process. So P2 over P1 is equal to 1. This term is going to cancel because the natural log of 1 is equal to 0. So all we have left is S2 minus S1 is the difference in the S super 0 term. So S super 0 at T2 is 2.6802. S super 0 at T1 is 1.6291, and the change in entropy then is 1.0511, and that's in kilojoules per kilogram per Kelvin. That's the units of entropy. That takes care of part A. Part B, Cp equals constant theory. This is from the TdS equations integrated. And the integration assumes that Cp was constant, so it comes outside the integral, and the integral on temperature gives us a log of temperature ratio and a log of pressure ratio. Well, the pressure term is also going to be killed just like in the first part because the log of 1 is 0. So we have the entropy change is going to be this term here. We need C sub P, and we're going to use, and we're going to evaluate this. We're going to take an average value at a T bar. T bar is the average of the two temperatures. It's the average of these two temperatures. I'm going to take 279 plus 773 and divide by 2. So we're going to look for we're going to look for C sub P at 526 K. The table we have for C sub P is table A20, and be sure to tell your grader which book you're talking about. Let's see, is this what I want? That was the previous table. Here we are. Here's table A20. Ideal gas specific heats of several gases. Air is here, and temperature goes down this way, and C sub P is the first column. I guess this isn't the clearest table. C sub P is the first column, and we're looking for 526. It falls in here, so we're going to interpolate between 1029 and 1040. This is what we're going to interpolate here. Let me go back to the page and transfer those values. I can scroll here. I want to talk about K values and Cp values from the table. So backing up a little bit, we've got values at 500, 526 is what we're looking for, and then 550, the values from the table where the Cp was 1.029 at 500 and 1.040 at 550 kelvins. And this is a good way to keep track of your interpolation so that somebody else can figure out what you have done. And then, of course, the interpolation is this distance in ratio with this distance gives me the mathematical relationship on the other side. So when I interpolate, I get 1.035, and you can check me on that. All right, to actually compute the delta S then, S2 minus S1, coming from this relationship, it's going to be the average specific heat, which is 1.035, and the units are kilojoules per kilogram per Kelvin. And then the natural log of the temperature ratio, T2 is 773, T1 is 279, and these must be absolute temperatures. And when I compute that, I got 1.0547, and again that's in kilojoules per kilogram per Kelvin, the units of entropy. And that is responsive to part B. Now, the answers to part A and part B don't agree. What's the percent error? The part A response using the gas tables, the cables were constructed with the specific heats can vary with temperature. So the integration is carried out more completely. So I'm going to use the value from part A, 1.0511, as my best value. I'm going to subtract 1.0547. I'm going to divide by the value that is the best times 100%. My percent error is minus 0.00346, or 0.346%. So these are close. And the reason that they're close is that the C sub P changes slowly. with temperature. And we could see that if we jump back to the other table for a moment. At beginning state, the C sub P value is something like 1.005. At the end state, 700 something, the value is something like 1.08. So it changes by maybe 8% over this range. And then we found an average value that helped us out. So C sub P changes slowly. Then the approximate, this one here is the approximate calculation. And engineers need to know how to work with both precise and approximate approaches. All right. Yeah, you may not have the table available. This is why the approximation is handy. And there's certain analytical things you can do with the approximate value. All right, so the recap. This is an example. We're looking for the entropy change for an ideal gas. And we're going to use the gas tables and the theory. You can always pull in the gas law for these calculations. The gas table requires that you use S super 0, which is not entropy. It's an entropy at a standard state, which usually needs to have a fix-it-up term for the pressure. The CP equals constant theory. We don't need to use a table for S super 0. We do need a value for C sub P. So we use a different table for that. So, which you choose might depend on which tables you have available. And to do a better job, and we came out very close, we used the C sub P at an average value. Always tell me which table you're using. And then, if you remember, when you look for percent error, if you put the best value in the basement, then all will be well.